let us talk about the key modes of interannual climate variabilities that we have on Earth. The first one is the North Atlantic Oscillation. Okay. Here we go. The North Atlantic Oscillation reflects the interannual variability of the Northern Hemisphere westerlies. Okay, we're talking about the westerlies in the Northern Hemisphere at mid-latitudes. And we're talking about the pathway of storm patterns, of cyclones, of rainfall. Okay. And we can see from the sketch that there are significant changes happening between the positive phase and the negative phase of this oscillation. Okay, so during the positive phase, we have a significantly stronger westerlies, and we have a northward shift of the storm patterns and the patterns of cyclones, which implies enhanced rainfall over northwestern Europe during this time, and a suppression of rainfall or less rainfall in the Mediterranean region. So you have dry regions and wet regions. Okay? Similarly, we have wet conditions over the Western America. Okay. All right. During the negative phase, we have weaker westerlies, and the westerlies are more zonal and influence rainfall over the Mediterranean region, and there's less rainfall over northwestern Europe. Okay, there's also less rainfall here on northwestern America. Okay, these are the key features in terms of rainfall. Okay. Indeed, if you have a big storms, it also influences the temperature. Because you can have cold air outbreaks of polar air masses influencing the climate, both over North America and over northwestern Europe. Okay, you can see the big influence that this oscillation has on the climate in the region. So it controls the storm activity and precipitation extremes over North America and Europe. Okay. This mode of variability is actually a mode of internal atmospheric variability without ocean influences. So there is no coupling with the ocean happening here. And indeed it has a big influence on the economy. The link to agricultural production is obvious. But it also influences the ice transport, for example, from the Arctic Ocean into the North Atlantic. So it has also links to other climate feedback mechanisms. Okay, and so now how can you measure or reconstruct this mode of variability? You can use an index called the NAO index. It's defined as the difference of air pressures at sea level between two weather stations near Iceland and Lisbon and Portugal. The long-term value is subtracted. And this one is based on physical principles, so that differences in pressure are actually related to the strength of the wind, of the westerlies. Okay, it's based on first dynamic principles, which I don't teach you as part of this topic. Okay, but anyway, you can use measurements of air pressure, in particular the difference of air pressure, as a measure of the magnitude or the strength of a wind system. Okay, and if you do that, you can reconstruct the time series, which is shown here from 1870 to around 20 15, and you can see that there is a positive phase marked here in these red columns, and there's a blue marks the negative phase. Okay, and that gives you a feeling for what's the time scale, and how often do you have now positive modes as compared with negative modes. And you can see that sometimes you have longer periods where you're in the negative mode. Sometimes you have longer periods in the positive mode, and this is highly variable. You get lots of variations, but the typical time scale is 2 to 8 years. Okay. All right. So this is how you can reconstruct the NAO. And as you can see here in this image, it has the biggest influence on the North Atlantic region. There's a limited influence on what happens in the southern hemisphere. So let's talk about the El Niño Southern Oscillation. Okay. The El Niño Southern Oscillation, ENSO. Okay. So the El Niño Southern Oscillation is a mode of variability of the intertropical Pacific Ocean. Okay, it's to do with the Walker circulation. And we discussed the Walker circulation before, but it also involves the ocean. So let's focus on the average map shown here at the top. This is the average situation, and what we're looking here is the Pacific Ocean from the western side over to the eastern side. Okay, it's a vertical transect, and it involves the atmosphere and the ocean. Okay, so the link between the ocean and the atmosphere is the sea surface temperature. Okay, and we have the warm pool on the western side. So there are the trade winds that blow from east to west. The air takes up moisture, through evaporation, okay, and feeds into tropical convection and rainfall on the western side. And there's a return flow at height. So this is what we call the Walker circulation. Okay. Simultaneously, there is a process that we call upwelling on the eastern side. Okay. It's the upwelling of cold water to the surface and the nutrients which supports the marine ecosystem in this area and the fisheries in this area. Okay, it triggers plankton blooms and starts the marine food web in this area. Okay, so this is the average situation. However, every now and then there's an El Niño event happening, and this is called the positive mode. Okay, it's the positive phase. So what happens during this phase is actually there's a reversal of the trade winds in the western Pacific. Okay, it actually triggers a special type of oceanic waves, okay, that propagate over to the eastern side. Just mentioning it here. But what happens is that the warm pool extends over to central parts of the Pacific Ocean, and with that change of the sea surface temperature, the area of cloud formation and rainfall moves away from the west and moves over to central parts of the Pacific Ocean. Okay, simultaneously the upwelling disappears on the eastern part, so there's no more nutrients to feed the marine food chain, and so this one absolutely collapses. The fisheries and the biologic productivity in this area collapses. Okay, so this is what we call El Niño events. Okay, and the negative phase of this mode of variability is called La Niña. It's an amplified version of the average situation. Okay, looks like the average situation, but it's amplified. Okay? You have more rainfall, more intensive rainfall in western parts. And you can easily imagine how this influences rainfall patterns in the area. Okay. However, the El Nino Southern Oscillation can also influence the climate away from the equatorial regions, because it can trigger disturbances that move around the Earth along the equator and have some teleconnections to other modes of variability. Okay, this one is the strongest and the most dramatic one of this variability. So it controls the precipitation extremes in the western Pacific, indeed also reaching into the central Pacific, okay? And controls marine productivity in the eastern Pacific region. So let's have a look how these different modes look like if you look at sea surface temperatures. So let's go through these temperature distributions that are shown here, so that you can get a feel for the El Nino Southern Oscillation. So what's shown here is the famous 1997-1998 El Nino event, okay, which was at that time one of the strongest El Nino events ever recorded. Okay, noting that the satellite technology doesn't go back that far. But anyway, so what's shown here is the before the event situation of sea surface temperatures, and you can identify the warm pool. Okay, so red is warm above 28 degrees. Okay, you can see the warm pool, and you can see the appearance of cold water on the eastern side. This is the upwelling that we are referring to. Upwelling of colder water to the surface. Okay? So then, just after the event, there is this wave created moving from west to east along the equator and causing a warming along the region. Okay? It's actually not warm water that is moved over, it's just the effect of a wave that leads to this relative warming event all along the equatorial regions. Okay? And if you look at the difference between before and after, this is what we call an anomaly. You can see the relative warming that the El Nino event has caused. And this is significant. Yeah? We're talking about several degrees in a very large region. Okay? So this is shown on a sphere, here again on the top right, and then 1 year later, and 1 year later there's nothing seen. It's back to normal conditions. Okay, so that you get an idea that this event, okay, lasts for a year. Okay. All right, and you can also get a feel for that this actually has an influence on the surface temperature distribution. Okay. It has, and if you think in terms of global temperatures, and the Pacific is a relatively large contribution, and here's the link. So how can you measure it now? How can you reconstruct El Nino events over a longer time scale? Okay. So there are two alternative methods that you can use. Okay. One method is based on weather data, and the other one is based on surface temperature, sea surface temperature values. Okay, let's focus on the Southern Oscillation Index, SOI, is defined as the pressure difference at sea level between Tahiti and Darwin. It's shown here in this map. Okay, pressure difference. And this pressure difference is a direct measure of the direction of the trade winds, whether they go from east to west or whether there's a reversal from west to east. And based on that, you can reconstruct El Nino and La Nina events. Okay? So that's done here in this one, where the blue is referred to as El Nino. El Nino events, the blue one here. And that's the time series starting from 1982 to 2000. Okay, indeed, the meteorologic data go back much further. It's just chosen here so that you can compare it to the sea surface temperatures. Okay? So sea surface temperatures are based on the most popular index is called Niño 3.4, and it's based on sea surface temperature anomalies in this area, which is shown here by the black box. Okay, which is just historically, takes part of something that was called Niño 4, something that was called Niño 3. It just grabs part of each of these regions, and that's why it's called Niño 3.4. Yeah. Because what you get with an El Nino event is a warming in the central Pacific, and this is what you can derive from observations. You see these El Nino events are these events here shown in red, which corresponds to the ones shown in blue on the left side. And this gives you a feeling for how often do these events occur. And sometimes you have El Nino events occurring in subsequent years. You can see these conditions here over longer time periods. Sometimes you have more La Nina events. All right, so that's the famous ENSO. So for completeness, we should also look now at longer periods. Okay, if you look at temperature variability in the surface layers of the Pacific Ocean, okay, and you look at timescale of 100 years, you can actually see that sometimes you have warm phases where the temperature is up to 2 degrees warmer. Okay, sometimes cold phases where it's 2 degrees colder. It's not in the entire Pacific Ocean, but it's in significant areas. And this one, the time scale here exceeds 20 years, and this is what we call the Pacific Decadal Oscillation. And the reason why I show this is it's because it's linked to the El Nino Southern Oscillation. Okay, and how it is linked is, it's sometimes you have more El Nino events than La Nina events. So you have a warming phase over a longer time scale. Okay. Sometimes you have more La Nina events than El Nino events. So you have a relatively cooler phase. Okay, and this is what it is. Just show you how these positive phases look like of the El Nino Southern Oscillation and of the Pacific Decadal Oscillation. This is what's shown here. In the bottom, El Nino Southern Oscillation, El Nino. Okay, we looked at that before. Okay, this is how the sea surface temperature anomalies look like. Okay. La Nina, you can see the opposite phase, and comparing these two, you can see that there are regions which are colder and regions that are warmer. And the Pacific Decadal Oscillation looks very similar. Okay, and this is just to confirm what I said, that if you have more El Nino events, you essentially get into the positive phase of the Pacific Decadal Oscillation. So the PDO is the dominant mode of decadal temperature variability in the northern and central Pacific Ocean. You can see that there's big changes happening here in the northern Pacific Ocean, and it can be explained as the cumulative effect of subsequent ENSO events. And if you wonder about these arrows which are shown here in this graph, these are wind anomalies. So there's a link between surface temperature anomalies and wind anomalies. Okay, so that it's a coupled mechanism. All right, so the last important mode of interannual climate variability is the Indian Ocean dipole. The Indian Ocean dipole is also linked with the warm pool of the ocean. Okay? And this is shown here in sketches. So it's linked to precipitation variability in the intertropical Indian Ocean. So we're now looking at the equatorial tropical regions from the western side and to the eastern side of the Indian Ocean. And we're looking at temperature anomalies. Sometimes it's warmer on the eastern side, creating enhanced rainfall through tropical convection on the eastern side, colder on the western side. In other years, it's cold on the eastern side and warm on the western side, where you have enhanced rainfall on the western side. Okay, it has links to the El Niño Southern Oscillation. Sometimes events occur at the same time, okay, associated with variability of stuff related to the warm pool. Okay, it has also an influence on Australian rainfall in some regions. Okay, there are links to Australian rainfall. Okay, just a little bit more about the Indian Ocean dipole. There is a dipole mode index, the DMI, which is used to monitor the dipole, the Indian Ocean dipole. It's based on sea surface temperature values, the difference of these temperatures between these regions, the western region, shown here on this map, minus the eastern region. Okay, it's based on satellite data, and you just take the difference. Okay, and this time series shows you the west SST anomaly and east SST anomaly and the DMI index in blue, okay, which is the difference. And it's a time series here from 1988 to 2018. Okay, and you can identify events where you have cold water appearing in the eastern region. Okay, these are called positive IOD events, and there are 3 in this time series, and it's to do with this eastern region. Okay, these are eastern region. All right, let's just have a look at how it looks like in the eastern region during these events. What happens during these events? Yeah. In the southern hemisphere winter season, okay, that's what we're talking about. And this is shown here at the top. So during these strong positive IOD events, you get coastal upwelling. Cold water appears along the coast of Sumatra and Java. Okay, that's the upwelling shown here in temperatures. Yeah. In blue, cold, in red is the warm water, which is totally different to the normal situation where often you don't get that upwelling. The upwelling is suppressed. Okay, in terms of the difference map in temperatures, you can see the significant impact that these positive Indian Ocean dipole events have in terms of the temperature changes. And we're talking about temperature changes in the order of 1 degree. Okay? In a vast area. Okay. We're talking about, that's 1,000 kilometers, 500 kilometers by 1,000 kilometers. All right, so and what's the link? What does it do? Why do I show it? Because sea surface temperature has an impact on atmospheric convection, and if you have colder surface water, you weaken atmospheric convection, and with that weakening comes a change of the wind patterns, and that has a big influence on the monsoon winds. Okay, this is what we call the Indian Ocean dipole. So all right, and this concludes the second part of this lecture.